So you're online? Yeah? Okay. Hello, good morning, good afternoon. Welcome to the 34th Surface Ventures keynote webinar. My name is Dr. Subhajit Bhaumik, and I am International Ambassador for India at Surface Ventures. So, a short about Surface Venture. We are a non-for-profit organization, and our mission is to provide world-class material science education for academia and industry. So today, it is my pleasure to introduce our speaker, Dr. Carlos Lorenzana of Rimsa Metal Technology SA. So, brief bio of him. Dr. Carlos Lorenzana hails from Barcelona and has been passionate about materials from a very young age. He received his PhD in chemistry, material science from the Universitat de Barcelona in 2001 and his MBA in 2006. Since then, he has been involved in research with focus in tribology, both in public and private sectors. He joined RIMSA in 2011, setting up the R&D department, and since then, they have focused on expanding the knowledge of tribochemistry in this sector. So I would also like to thank today's partner, Artec Instruments. We will have a short presentation from Gregory Fivaro later in the event. We will also be releasing the poll questions and handouts from Artec. So as we go along, please type your questions into the chat and they will be marked for the Q&A sessions. So we are planning for 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So let's welcome our speaker for today and proceed with the webinar. Dr. Carlos.
Thank you, Dr. Bhaumik. Thank you for the kind introduction. And hello, everyone. Good afternoon, good morning, depending on when you are. Let me share the screen and start to talk about what we are going to talk today. We are going to talk about if size matter in the testing of friction materials. Friction materials, you will see, is one part of tribology, but is something that is not black and white and is really close to tribology, but with some tweaks. So today the conference will be around the influence of testing scale on tribochemistry and friction behavior assessment in friction materials organic basic formulations. So basically, just few words about who we are, about RIMSA. We are a SME innovative company, especially turning innovative ideas into business opportunities. We throw in the form of high added value materials and raw materials for three main sectors: friction modification, discontinuous reinforcement, so fibers for different kind of matrix, and then some materials for green energy production and storage technology. Today, of course, we are going to show some of our research and that is done in friction modification, specifically friction materials. We provide, we have more than 50 additives. We sell in more than 25 countries, and we have been in the market since 1985 now, so more than 35 years, almost to 40. And of course, we have a big focus on innovative on R&D to understand not only our materials, but how it behaves in the applications. And that's what we are going to try to show you today. And our three values are innovation, of course, inclusion and diversity. We are working in many countries, and we include people from many countries in our team. We need to understand the culture of every every different partner, and of course integrity, because we try to understand why the things happens, the reason why behind any additive. So this is what we consider is the best integrity you can have in this business. And of course, we are a committed company about quality and environmental protection. So in brief, assessing the stability of coefficient of friction. Why coefficient of friction is so important for friction materials? Basically, when we consider a friction material, I mean the material that is used in a brake that is fitting against a counterpart, that can be a disc, can be a drum. We have this friction material that needs to provide a stable coefficient of friction in a really high, in really very different conditions of parameters. Okay, so testing this friction material delivers several outputs, like the pressure sensitivity, the sliding speed sensitivity, the temperature sensitivity, the wear ratio. And so for coefficient of friction, we need this coefficient of friction, or we want this coefficient of friction to be stable, to be the same in every condition, no matter the pressure is, no matter the speed is, no matter the temperature is. And of course, the hard part of this work, of this engineering of scientific work, is to connect all this output that are engineered data with a lot of incredibly high amount of inputs. On these inputs, we have all the raw materials, we have the friction material composite, we have the percentage, the raw materials we use, the percentage of raw materials we use, the processing conditions and the manufacturing conditions, pressure, temperature, finishing, geometry, and so it's kind of really like a black box when you enter there, and you need a lot of testing, of very complex testing, and it's not always easy to understand why the things, or answer the question of why something is happening. No? So this requires a lot of testing and analysis, because these formulations, unfortunately, are not just engineering components. We are not just talking about a component with a structural properties that is made on steel and have a geometry. No, unfortunately, this is much more difficult. So during all the evolution of friction materials, the evolution of braking, there have been like three drivers, or we may see some three drivers right now that are driving the evolution of friction material. One is the restriction in the use of chemicals, of course. Yeah, the brake emission reduction, and the changes in powertrain due to electrification. All this change the condition of pressure, of temperature, of speed, and of course, then we are changing some of the inputs. So probably some of the outputs are going to be different. So we need higher need of correlation between these engineering results and the material science results. No? So this means we need more testing. We need to do not only more testing, but more characterization of what's happened. And this brings to higher development cost. So in this sector, the big inertia dynamometers are the workhorse of the friction industry, because to get all these outputs with different speeds, with different pressure, with different temperatures, and simulating the inertia of the vehicle, we are trying to stop this kind of equipment that works with a caliper, that works with the brake pad, and works with the rotor, or works with the drum, are the workhorse, no? But are expensive and are expensive to operate, not only to acquire and to install, but also to operate, because we need to work with a rotor. There are long tests and so on. So in the last years, these tribometers, like the one we have, the MT-5000 from ERTEC, are becoming useful tools for R&D. But we need to understand, and this is very important, to translate these outputs that we can have from a tribometer to correlate. If they correlate, the question is, do they correlate with the results we get from a dyno? And this is not only in terms of friction behavior, but also in the tribochemistry. If we are able to reproduce the same tribochemical processes that take place in the surface of a brake pad and a brake rotor. That's why the question of dosage matter when thinking friction and tribochemistry. So today we are trying to give some answers and some clues to this. This, what you have here, is just an example of what it can be a characterization of a friction material. You can see that there are different sections. This is a dynamometer test. In this case, is taken from a J2522 schedule, and you can see how we have different speeds with a fixed pressure, or then we test with different pressures. We test in a specific speed, or we do a number of different stops of going in a specific deceleration rate from a specific speed, but increasing the temperature of the rotor, not letting the system to cool down. And or we can do this again, this temperature, we can increase the temperature of the rotor and then measure on these same conditions of characterization here, but in different rotor temperature, or then we can do the efficiency, the effectiveness, the same at different pressures at this high temperature. So as you see, the testing conditions are very complex. The outputs we measure are in very different, in a wide range of different parameters. So this is important to understand how this correlates. In this case, we are going to show initially some results of a much simple test than this one, but basically it's the R90 VDA 285 that this has these 8 different sections of testing that goes through different speeds, pressures, temperatures, and so on. Here is the profile of the temperature, and this is the response you should have. You have the response of the coefficient of friction at different temperatures. So we have, of course, we do our work in the tribometer, but also we try to correlate with full-size dyno. In this case, you can see how this the coefficient of friction. In this case, this is the same friction material tested against a gray cast iron rotor. In this case, this is what we get with the full-size dyno when we work on this schedule. This is what we get with the tribometer, and this is pretty close. We have a good coefficient of friction profile correlation between the full dyno and the tribometer, and we have achieving also these different temperatures on the we are able to replicate this on the tribometer. Of course, this is very important. The fact of having not just a pin on disk, but a fully programmable tribometer where we are able to program different speeds, but not only different speeds. We can program different decelerations. So we can simulate the braking, we can simulate the snoop, so the reduction of speed, and we can achieve the temperature we need because this change, and you will see later when we talk about tribochemistry, this change, how the surface of the brake pad modifies in every section, and this is what it correlates with the coefficient of friction we obtain with the engineering data. So this is very important, and having the confidence of that we are able to simulate, we are able to replicate these coefficient of friction profiles in a tribometer allow us and allow the community of friction to have an initial assessment at a lower cost and a higher speed for development purposes. For example, in this case, what you see here is this same profile, BDA 285, but in this case with the same formula, but using different rotors. In this case, you see how this formulation A, this is an AO formula, it gives a different coefficient of friction profile when you work with a gray cast iron rotor, or when you work with a laser cladding coated rotor made of nickel chromium boron silicon and tungsten carbide, or a HBF thermal spray nickel chromium boron silicon plus tungsten carbide, or HBF with, in this case, this is a titanium carbide with stainless steel. So this gives you a lot of flexibility to work with small samples, but having the confidence that the profile you obtain will be something that will be close enough to the one you are going to obtain on the dynamometer. And this is the same case for, you can see here, if we use a different formulation, or we can compare different formulations with different rotors in this case. We have here a hard-coated rotor with titanium carbide and with a formulation B. And you can see how the formulation B with the same rotor behaves in a different way, and how they compare with a gray cast iron. This is completely different in a gray cast iron with a hard-coated rotor. This is one of these trends right now going for emissions. Emissions are implementing the fact to reduce the emissions in the brake pads is making the industry to test and try to implement some coatings on the rotors. And what is something that can be not working with the traditional materials and that you have in the rotors, like gray cast iron, may be working on when you work with coated rotors. So this kind of tools, this kind of the tribometer, give you a easy tool to simulate and to go through and do an initial screening. These are the engineered results. But the important thing for us with a tribometer and a dynamometer is to understand if we really have the same tribochemistry. And what is tribochemistry? Tribochemistry relates to the mechanically initiated chemistry. So chemical reactions that take place in the boundary layer, and the process involves the formation on a film on the contact surface. This is very important on the friction materials. Friction materials are commonly, the organic friction materials usually are, there are like a phenolic resin matrix, so a polymer that includes a huge amount of different kind of additives and minerals, metals, different charges there. So and of course, as you have seen, this is breaking up to 500 degrees, up to 600 degrees of the temperature on the rotor. So phenolic resin degrades starting from 400 degrees. So we have a lot of phenomena there that are related to the degradation of the phenolic resin and how the debris that is generated because of this is generated, and this is why it contributes to the coefficient of friction stability. So this transfer film, if we take the cross-section of a brake pad and we see the working surface, we are going usually to find this kind of tribofilm. This is something that is related to the tribochemistry, so the mechanical induced reactions that take place on the surface of the rotor, on the surface of the brake pad, and all these debris, and how these debris are incorporated or are kept or are released from the surface of both the parts. So it's very important for the tool we use for to assess the coefficient of friction and to do the research that is able to replicate this tribochemistry in the same conditions or in close conditions to the one we are going to obtain in a big measure machine or testing machine like a dynamometer or in the car. what we are going to obtain in the curve. So these results we are going to show you, it goes in this direction. No? This tribofilm can be of different. These are different cross sections of some work we have done, and of course these transfer films basically when we are working with conventional friction materials and we are working with conventional cast iron rotors. Usually there are these transfer films that we found can be of 4 types, let's say. 3 of them are, we have a transfer film that is based on iron oxide, basically. This iron oxide usually came from the rotor, from the oxidation of the rotor, and then it builds up this transfer film, and we can find this, what we call the loose transfer film, so with big particles of iron oxide and other debris that may come from the pad. We have what we call this compacted transfer film, so it is a more iron oxide, very small nanometric iron oxide debris, so with a very long period in the residence time in the thread body layer, and that are stacked here. This can be this mixed transfer film, so we have some areas that are compacted debris, some areas that are loose debris, and we may have also the possibility of not having any transfer layer on top of the brake pad. Sometimes, depending on the formulas, you don't get this thick or thin transfer film. So, but tribochemistry also happens not only on the surface, but it happens also in the it happens also beneath the surface. We may have some additives, some chemicals on the composition, like the phenolic resin, or other additives that may be reactive to the environment where the friction takes place. In this case, one important additive of this type are the sulfides, for example. Sulfides are used in the friction materials to stabilize the coefficient of friction at high temperature and to reduce the wear. But you may see here how a sulfide usually reacts with oxygen, and every sulfide has a different temperature of reaction. In this case, we are showing some results of the iron sulfide, and the iron sulfide reacts with oxygen around 400 degrees. And you can see here how after a testing on a dynamometer, you can see how the signal of sulfur has gone in these first 200 microns beneath the surface. So in some extent, this iron sulfide has been reacting beneath the surface, beneath the working surface, and has become iron oxide. So if this happens on the dynamometer, it's very important that this also happens on the tribometer, and make sure that this happens on the tribometer or the pin on this or whatever lab scale tool you use to assess a friction material, in order to guarantee that the results we are getting from the coefficient of friction, from the engineering results, are going to be easily correlated with the results we may obtain for a big testing equipment like a dynamometer. So you are going to see a brief comparison with a formula. In this case, we are going to use the sulfides as a marker to follow up this reactivity beneath the surface or in the surface of the brake pad, and we'll compare what happens in a dynamometer, in a friction material tested in a dynamometer, and the same friction material tested in a tribometer. For this, we are going to use 2 different sulfides as a marker. One will be the iron sulfide, and one will be one composite sulfide that is a core of iron sulfide with a coating coated with tin sulfide. What it makes this gives a different oxidation profile for each one of these 2 sulfides. Okay, what you see here is a TGA, DSC TGA, and what you see here is how the iron sulfide reacts with oxygen to get oxidized. This is something that happens in between these 400 and 600 degrees, and in the presence of oxygen, of course. Instead of that, this composite, we call the SFO5, this composite, you see the TGA, the DSC, we see that the reactivity starts at around 450 degrees with the oxidation of the iron sulfide, takes place up to 700 degrees, and then we have the oxidation of the tin sulfide to tin oxide. So two different oxidation profiles, two different temperatures where this oxidation takes place. And we are testing these two materials, these two different additives in the same formula. So we are making two different friction materials that everything is the same except the sulfide used. In this case, we are using a 5% in volume of the iron sulfide, right? Or the composite, the SFO5, SF50. Now, iron sulfide, tin sulfide composite. We see that the difference since in coefficient of friction, these are the results of the full-scale dynamometer. So this is the real test. It's not really different, especially at high temperature. The response of using the iron sulfide or the composite in this particular formula, the engineered results is basically the same. So we have basically the same coefficient of friction. The difference is if we measure the wear of the brake pad after this test on the dynamometer, we see that at 400 degrees, this is what we see here is the wear in millimeters of the brake pad happening at 150 degrees, happening at 300 degrees, happening at 400 degrees. When we use this composite, this iron tin sulfide, we have a lower wear at high temperature compared with the pure iron sulfide. When we use this FES, the wear is higher. Why the wear is higher? That's something probably related to this tribochemistry and is related probably to the oxidation of the iron sulfide at high temperature. We are getting iron oxide. We don't have anymore the iron sulfide at high temperature. So we are not getting this effect of lubrication or this effect of wear protection of the sulfide at high temperature. But how to assess this and how we can follow if this is happening in the dynamometer or the tribometer? We have done a test, a simple test to follow that. You are going to see the different charts. Right now, all the red ones are always from the dynamometer and the green ones came from the tribometer. So we have assessed, sorry, because this is a mistake here. This is around 10 square centimeters. This is the brake, the coupons we mount on our MTF. So what you get is 10 square centimeters of friction material that are tested against a rotor that in this case is Hungary cast iron, the same that we will use in the dynamometer. And what we have gone is through a process of 200 stops at each temperature, in this case the 150, the 300 degrees, the 400 degrees, in conditions of 30 bars of pressure, going from a speed of 100 kilometers to 0 kilometers per hour, so a complete stop, and a deceleration rate of 0.4 g. And we are going to see this, how the coefficient of friction evolves and the tribochemistry evolves both in the dynamometer and the tribometer. So basically, this is a summary of what we have get in the four tests. We have the full-scale dyno, and we have the pad screening tribometer, in this case the MTF 5000. And a full-scale dyno, we have tested the formula with iron sulfide and the formula with iron and tin sulfide. And the pad screening tribometer, we have done the same. And we have tested at 150 degrees, 300 degrees, 400 degrees. So we measure basically the coefficient of friction and the temperature we have achieved at each temperature. You can see how a full-scale dyno, this is the rotor temperature, the temperature on the counterpart, on the cast iron rotor on the surface. So we have basically we have achieved the slightly different coefficient of frictions and slightly different temperatures, but they are close enough to be considered like we are in the same range. So the total average coefficient of friction is we may see the same trend. We have this. The average coefficient of friction increases a little bit when using the composite sulfide compared with the iron sulfide, and this is the same case both in the full-scale dyno or the pad screen tribometer. You will see here in a more visual way, this is the evolution of the coefficient of friction of in dyno and in tribometer in green. And here is the average of the coefficient. This is for each temperature, the evolution, and this is the average. So we can see in some extent that in the dynamometer and when we compare the different sulfides, we are getting the same trend when if it's in dyno or in tribometer. Okay, and if we go to the detail of how this coefficient of friction of the friction material and the rotor evolves, we will compare here the results in red of the dynamometer of the full-scale dyno with the in green here the results of the coefficient of friction evolution on the tribometer. You can see here the comparison at 150 degrees with iron sulfide. You see how this. We start here are the 200 stops, and here what you see is the coefficient of friction line in the dynamometer, and here is the evolution of the coefficient of friction line in the tribometer. So you see this particular drop in coefficient of friction is being replicated in the dynamometer and the tribometer. Here, these lines are the evolution of the temperature that in this case, because of represents, we are showing a separate line. Here are the results of this iron sulfide at 300 degrees, and we have also a close coefficient of friction, and also we have this drop. There is some slight variation, but we see this evolution of the coefficient of friction. So there is some tribochemistry going on here. And at 400 degrees, we have a very, very good correlation in the evolution of the coefficient of friction on the full-scale dyno and the tribometer. And if we go to understand what's the tribochemistry, what happened on the tribochemistry on the full-scale dyno and the tribometer, if we do the map, the elemental distribution map from the surface in the cross section of the brake pack, we are going to find that the signals of iron are. We found this the elemental mapping shows that we have the oxidation of iron sulfide taking place up to 200 microns beneath the surface. So we have the same tribochemistry. We have this 200 microns. After this 400 tests, we are getting this iron sulfide that is being oxidized. If we analyze with SEM the cross section, the region on just nearby the working surface, you see that all the iron particles gets the signal of the iron containing particles are iron oxide. So we are being able to replicate this oxidation in the same way in the dynamometer and the tribometer. If we see the results with the composite with iron and tin sulfide at 150 degrees from the dynamometer and the tribometer, we have this close profile of the evolution of the coefficient of friction. At 300 degrees, here we see a difference, but still we have this small drop. Here the drop is bigger, but then the coefficient of friction is pretty close. And at 400 degrees, we have a slightly different here in this initial area. Here with the tin sulfide and iron sulfide, is not as pronounced, as it's not as clear the correlation as with iron sulfide, but still we get a close result. And if we go to analyze the elemental map distribution on the surface after the dynamometer or the tribometer, we see here that there is not oxidation, neither on the iron sulfide, neither on the dynamometer or the tribometer. So we are, and if we analyze this with a SEM, we are going to find that the particles of the sulfides are still giving the signal of tin sulfide and iron sulfide, both in the cross section after the full scale dyno or the tribometer. So we can correlate. We can say that we are obtaining the same coefficient of friction profile because we are sure that we are keeping the same tribochemistry. We are able to replicate this tribochemistry that takes place beneath the surface. And we may say, as a summary of these results, that with the full scale dyno, we in this, neither in the iron sulfide formula, neither on the iron sulfide tin sulfide formula, we don't have any pad transfer field type because this formula don't generate this transfer film. And the oxidation, after this 400 degrees test, the oxidation depth achieved by the iron sulfide is around 200 microns, both in the full scale dyno or the pad screening tribometer, and we don't have any oxidation of the composite of iron sulfide and tin sulfide, neither on the full scale dyno or the tribometer. Remember that the oxidation of the oxidation of the iron sulfide on the composite, because of the structure, was not happening very fast at 400 to 600 degrees, but started at higher temperature and ended at a much higher temperature. And with this, we are going to finish, and we are going to go to the main conclusions about this. If the size of testing is important for friction materials. It's true that the testing, as you have seen, and we have go through, the incredible amount of inputs we may have, and the outputs we need to measure in very different conditions, makes that the testing a friction material is still very much required to validate how a friction pair behaves in working conditions. And this increases the development cost, especially when radical changes in formulation happens. If we are in a transition, it needs like the electrical vehicles that works in a different temperature conditions or with different corrosion behavior. It increases the needs of testing. So in this scenario, the pad screening tribometers are developing tools, are developing themselves in a new tool to reduce the testing cost and speed up these development cycles, because they're low running costs and the easy setup. A test that takes hours or days in a full dynamometer, because you need to cool down, and in each session you need to cool down, is in a tribometer we can speed up. So all the mass involved in the testing and the cycle is much shorter in order to run the cycle. So performance and wear is dependent, of course, on the tribochemistry phenomena taking place on the friction per surface and interface. So you have seen that we have this transfer film, and this transfer film, we need to generate these reactions to make sure that the engineered results we are getting from this test can be correlated in between a tribometer and a dynamometer. So being able to replicate these tribochemical reactions in the interface is a must to ensure the correlation. And the work presented today in this study shows a good correlation between not only the coefficient of friction, and this is very important, the tribochemistry on the path after the test at high temperatures. For us, it's very important to make sure to work with enough surface of friction material. In this case, we are using around 10 square centimeters to be able to achieve the temperature on the surface of the brake pad and the rotor, the same temperature only by friction that you achieve in a car or you achieve in a full scale dynamometer. And within that, with the use of these results, should contribute and are contributing to the development of those brass screening tribometers in a everyday tool for the friction community, especially on these days where, again, electrical vehicles, changes on the restrictions on chemicals like copper, like antimony, like tin in the future because the price is so high, and the introduction of these emissions requirements, so the introduction of hard-coated rotors, FNC-coated rotors. So everything is changing. So this is becoming one interesting tool and for the not only for companies like us that we are always developing new additives for the friction, but also for companies working with friction materials in the production. So that's all from my side. Thank you so much, and everyone in the audience, if you have any doubt, you can write me to this email, cla@rinsat.com.
Okay.
Thank you. Thank you, Dr. Carlos. And maybe we can take the questions later after Gregor. And for the audience, I have shared the polls, and we have the poll results. We have 36% interested in brake pads, 36% with the brake pads alone, and rotors also. So your talk was very informative,
Thank you.
Dr. Carlos, and thank you for sharing. So now I invite Gregory Favaro from Artec to present, and then we will be taking the questions for the speakers.
Okay. Hello, everybody. Thanks a lot for joining this webinar. Thanks a lot, Carlos, for the nice presentation. I will introduce AirTech instrument tool and the possibility of multifunction instrument. AirTech, we are a US-based company, and we are developing and manufacturing advanced mechanical and surface testing instrument like scratch, tribo, two roller. I will show you later some slides. As I tell you, we are a US-based company in San Jose, US-based. I'm in fact based in Switzerland on the European base of our AirTech. We have office in India, China, and Japan, and we use a sales partner. In fact, we are proposing multi-functionality tools. And what we want to do is to offer the possibility with our tool not to do only one analysis, but to combine a lot of technology and to combine a lot of measurement characterization. It's why, in fact, in the past, we start with wear and friction by tribology. After we had scratch testing, we add indentation, we add also a 3D microscope linked to the system for roughness topography. And we also add spectral reflectance for coating thickness and optical constant. All the tests here can be combined on the same tool at the same time, and we can, with this product, learn much more than only doing one test. The main product line of AirTech instrument is multifunctional tribometer for friction wear. We have three different type of instrument: MFT 5000, 2000, 3000, depending load, depending option. We have an SMT 5000 for scratch and indentation tester for harness, elastic modulus, adhesion, scratch resistance. We also have a full range of fretting tester. Fretting is from 5 micron up to 2.8 millimeter, with a frequency going up to 300 hertz on small displacement mostly. As I say on my previous slide, we are also developing our own universal profilometer head to analyze all our data and surfaces. We have a vacuum materials tester. In fact, we can do tribology non-tension scratch in vacuum, but we have the same tool for high pressure for compressor application, for example. We have rolling, sliding tribometer, two roller, three roller for pitting, for fatigue, etc. Airjet erosion tester and CMP polisher. The main topic today was a multifunctional tribometer. It's why I move fast on MFT. And we propose a wide range of tribometer, and we can, with our tool, apply from less than 1 milliNewton up to 10,000 Newton with our MFT 5000. We have different motor, harmonic drive. We have fast motor. We're going from 0.001 RPM to 10,000 RPM. What is very important, especially for brake testing, we have now different motor, and we have one motor going up to 62 Newton meter, in fact, as a speed of 2,300 RPM, meaning it offers a lot of possibility to test with high torque. All our tribometer are very modular. We can, on the same system, use rotary drive, reciprocating, block on ring, disc on disc, ring on ring, and a lot of other configuration. We have a linear reciprocating going from 0 to 80 hertz of frequency. Naturally, a lot of environmental control for minus 120, and we can go up to 1,200 degrees. And we have also some humidity chamber to go from 5 to 95% of humidity. Naturally, all the tool, and Carlos explained well before about the SAA standard, we follow a lot of multiple ISO, STM, and DIN standard. Or it work. We choose a base, MFT 5000, 3000, 2000, depending the final load we want to use and all the mode. After we will choose on the machine, maybe we have a rotary, linear, long stroke, block on ring, fretting, or upper rotary drive. We choose the environmental condition from salt spray 500, 1000, minus 120, minus 60, or 1300. And we combine all the options on the same tool. What is also very important is the fact you can start with one option and add option every year, every 2 years, every 5 years, in order to have more and more capability with your tool. The idea to have something new with tribology was the fact we combined 3D profilometry with our tool. And for example, here we have a reciprocating wear. We are testing some steel materials, and we decide to take a picture of the stroke every 10 minutes. And you see 0 minute, 10, 20, 30, and we took an image automatically synchronized. It means you start with your linear reciprocating test, you move back to the microscope, you come back and you restart the test. We have, with a 150-minute example here, we can measure the volume wear progression, we can measure the roughness change, we can check if we have crack initiation, debris creation, topography change. It gives you much more possibility than basically doing 150 minutes directly and analyzing at the end the full test. You see here the increase of wear during the 150 minutes, and with the debris, with the large wear, from where it's coming, do we have hard particle? We can check really the lifetime. We can do multiple profile in order to understand the wear rate of every 10 minutes and combine on a curve to have a really related test for wear rate. As I tell you, Carlos showed a demonstration with a special pads with 3 coupons on the rotary drive, but we can also do basic pin on disc, ball on disc. We have a rotary motor. We can go to high speed. I tell you, we can go to 5,000 Newton if needed. We have high torque, slow speed, and we are doing this type of test quite often. As an example, you see here it's a cast iron rotor with 150 micron of Inconel on the surface. We cut really a rotor. In fact, we fix it on a metal plate and we are doing our rotation. And during the rotation, you see we have some decrease of friction every time. It's when we cool down because we move to the microscope. We have a friction coefficient at 0.69. We apply 50 Newton with a 60 millimeter diameter. It's really ball on disc on this type of rotor with a speed of 1,500 RPM. And here you see clearly the increase of wear during the test and the final wear at the end of the test. And this one helps you to understand clearly what happened in rotary one. We have a fast linear stage like here, and here we can choose in our software to change the frequency by step, to change, maybe we start 1 minute at 2 hertz, 1 minute at 5 hertz, 1 minute at 10 hertz, 1 minute at 20 hertz. You can really change a lot. We go from 100 micron to 30 millimeter. We can go up to 80 hertz in frequency, and we have an LVDT encoder on the back to measure also the distance. And this one, again, if I show you a small application, if we are doing linear, we measure with linear reciprocating both direction, meaning the friction on positive and friction on negative. And it allows us to do naturally some curve the displacement in function of the friction, but also here an example again on the same brake pads before. We use 80 Newton, pretty high load with a big ball, 3 hertz of frequency, 1,000 stroke with 8 millimeter, and we can differentiate different materials when it works in linear mode. Again, after the end of the test, we just scan the surface. We can compare. You see here the two materials use the same, have the same trend, except maybe at the end, the green one, sample 2, has more friction. But when you compare the wear scar at the end of the test, you see here we damage completely much more in terms of depth, the sample 1, but much wider, the sample 2, simply because it's harder and we break much more, we wear much more the ball during the test. We can also add option for block on ring. Block on ring, it's another direction. We are turning vertically, we apply a block. We can go up to 5,000 RPM. We have a torque inside the motor and we can go to maximum 550 Newton meter. Again, some curve showing the same friction in function of the time on a thermal spray on steel ring with 50 Newton. A big advantage of our MFT 5000 is the possibility to put an upper rotary module. And we are really unique on this functionality. The fact to put an upper rotary drive, we can do disc on disc, 4-ball, twist compression, thrust washer, a lot of testing. We can go up to 5,000 RPM with a max torque of 14 Newton meter. And the idea is in fact to block the lower part in order to maybe control differently the temperature environment. You see a small video. The upper drive is turning. It's a rotor, and we press on the brake coupon fixed on the lower part. Automatically, we move to the microscope. We scan the surface. We come back and we restart our test. And using, in fact, fixing the brake pads on the lower part will allow you naturally to analyze much deeply the coupon during the test. And here is the test we did. It was some coupon with 635 millimeter of diameter. It was a cast iron disc. We go up to 300 Newton as the diameter of the brake pads were a little bit smaller, and we reduce, in fact, from 2089 RPM to 787. It's a deceleration from 80 to 30 kilometers per hour in order to understand what happened with the materials. And you see here, at the beginning, we don't have so much defect, and we increase during the test, we are removing some materials and we are changing the topography of the sample. And we can do that because we have the upper rotary drive link with a 3D microscope. We have also a possibility, important possibility, is the fact to scratch with our head or with our upper loading cell. We can do nano, micro, macro, and we can add some sensor like acoustic emission, electric contact resistance, or temperature sensor if we work like that. What is for me important when we scratch, we use mostly progressive load from a low load to high load. And you see here an example on diamond-like carbon coating. We are removing the coating by a bad adhesion in this example. But you can also do some scratch hardness. A scratch hardness, you will scratch a constant load, you will measure the width of the scratch, and if you divide the load with the residual width, you will have, following the ASTM G171, the scratch hardness. It's a direct comparison between the weakest hardness, except we are much more statistical because it's not measured on one point. This one, you see, it's an example. We have a 10 millimeter scratch here. But we use also scratch, and it's very important. We can go to super high load because we don't have so much limit on scratch, and we can also scratch up to 500 Newton if needed. But it's sometimes very important if you want to scratch tribofilm on your brake rotor. During the scratch, we are monitoring the load, progressive load, we are monitoring the friction and the penetration depth, residual depth. And what happens when you increase your friction, you change layer, and when you change layer, you directly acquire the LC, critical load. You know the load, the first one was 3 Newton, second one was 6 Newton, and you see directly the residual imprint with a confocal image because we record with our 3D imaging. And to finish, the last possibility is directly to combine with an instrument indentation head with micro or macro head. You see here we fix Berkovich or Vickers indenter, and we are able directly after the test to measure, in fact, the hardness, HIT, the standard elastic modulus, EIT. And finally, you see here the superposition of the curve we analyze, the contact point, and here's the statistic between indent and the value we have. Naturally, we can always, again, move to the 3D microscope and analyze the shape of the indentation to check if we have crack, if we have deformation. I think for the MFT 5000, it's good for today. If you have any question, you can always visit our website or contact us. You will have my email with the presentation. And I think it's good for question now.
Thank you, Gregory. Maybe it's now time for the questions. So we have a few questions here for both Dr. Carlos and you. So let me mark one by one.
Yeah.
Yeah. So the first question goes here. Uh, why were high pressures used for testing, and how do they relate to practical application condition? Question from Mohammed Ryan Hashmi.
Answer live. Okay.
Yeah.
Okay. Yeah. Yeah. The high pressure are used in order to correlate with the testing that are done in the dynamometers for this kind of friction materials. You need to go up to, you need to simulate up to 90 bars or 80 bars on the surface. So that's why we use this.
Okay. So the next question. You correlate the COF and oxidation, but what about the surface topography or roughness modification? Question from Muhammad Dor.
Yeah, that's an important point. Usually, we don't have installed the the profilometer on top, and it's true that this is a interesting characteristics to measure, but in this case for us, because this is specific, for us the important thing to validate the tribometer was to make sure that the tribofilm and the tribochemistry is the same. This is something that you can see from the surface, but in our experience, it's always better to go to the cross section. And it's more important in our case to see the cross-section because our additives usually are reacting beneath the surface. And for us, it's important that. Usually, if you get the same tribochemistry, the topography is going to be the same. We are measuring this, but we are not showing this on this particular webinar.
Okay. So the next question from June is the temperature heat generated during the test is linked to the size of the brake coupons, and therefore the.
In general terms, yes. That's why we like it, and I think they also ERTEC is doing some better upgrades now with bigger motors, because this is one of the things we want to have closer to the dynamometer. You want to generate all the heat by the friction, and the heat you generate by the friction, because the size of the rotor is always the same, you need to the bigger the size of the coupons, the easier is to achieve the temperature. We are reaching now up to 500 degrees when working with low steel formulas. That is pretty close to the things they obtain in the industry, in the dynamometer. And the bigger the size, the easier to get to higher temperature. But of course, the higher the torque you require. So there's always a balance. We are working now with these 10 square centimeters. If we go with more surface, we may overpass the torque in some sections, and then you can play with this. There, for the smaller, I will say, tribometers for brake pad screening, for us is you have a very small diameter. Not only you will have problems with the temperature you achieve, but you will have a lot of influence on the edge. You will have a lot of edge compared with the surface of your friction material. So in this case, talking about tribometer, size matters about the surface you have for your coupons.
Okay. One more question from Mohammado. What is the expected torque on the dynamometer for this brake test?
This is a data that really, because I'm not involved on the testing itself, I'm not sure about that. I think has been explained also by Gregory when he actually said the capabilities and torque of the new equipment that is available.
Okay. So the next question: industrial dynamometers and some pad-sized tribometers can collect particles. Did you analyze those particles and saw any difference?
Yeah, not yet. Not yet. That's the question. We have not yet measured the. We see this through the tribofilm that is formed. Usually, if you get the same tribofilm, you may think you will have the same kind of particles, but this is something that we have not measured yet, and now it's very important because the emissions are measured in terms of number of particles. For different PM10, PM2.5 for the weight, but also the number. We are thinking to couple some detector to this, but not yet. We have not yet measured this.
Can I add some just one point?
Yes, please.
We deliver the system with a collector, in fact, to collect the particle, and we are working on a tool to analyze the particle film now, and it will be a solution end of this year, beginning of next year maximum. It means we know it's important for the new standard, and we are working on it. But it's a way to collect particle to be correct, and it's not but a simple machine, and you have good data directly. We have to do it on the right way.
Yeah.
So next question, Dr. Lorenzo. There are many questions in one question. What was the process to produce the sulfides?
That one I cannot answer.
Yeah.
Sorry.
So has SNS a better oxidation resistance from FES and FE?
Yes, as I show in the TGA DSC, the iron sulfide oxidized from 400 to 600, and the tin sulfide oxidized over 700 degrees. That's why usually tin sulfide is very suitable for really high temperature wear reduction, because it keeps in a state of tin sulfide and reaches the surface as a tin sulfide.
And were the friction layers on the pads comparable when coupled with coated and uncoated bricks?
These are completely different. We have show some other results about that in Eurobreak and CE and so, and the friction layer is completely different. As I say, friction films are mainly based work with the cast iron rotor. Iron oxide. So we change the material of the rotor. You have something like nuclear resistant based on titanium white or based on some other alloys. You don't have this iron oxide from the rotor, and the structure of the biofilm completely change. And this may affect the friction profile of the metal coupled with the
Okay. We'll move to okay. One more question is: did you observe any impact of tribochemistry on the debris size?
no, as I say, not yet. This is something that we have not yet measured.
Yeah.
Not yet measured the size of the debris. We measure, of course, the wear, but not we have not yet been able to focus on the side. There are now one of the strategies for emissions. Emissions are regulated being a PM10. So if you are over PM10, if your particle debris is 20 microns, this is not an emission. So there are some studies going on this direction for additives to modify this and so, but we have not yet measured and being involved in that.
Thank you, Dr. Carlos. Gregory, the question comes for you now. Is it possible to upgrade up to 10,000 RPM with the same frame of on MFT 5000?
We have motor going up to 2,000, 3,000, 5,000, 10,000. It's not a problem to upgrade for the speed.
Yeah. Okay, the next question. I think this is okay. Can you measure the profile in situ of wet lubricated contacts during a test, or would these need to be cleaned with solvent before the profile is taken? If the components need to be removed and cleaned, how do you ensure correct alignment when replacing the components back in the test rig to continue the test profile?
It's an interesting question. Thank you. The profile in situ, I will say yes and no. It's depending the lubricant we use. With our lambda head, we are able to do 5 different modes. We have white light interferometry, NIPCO disc confocal, bright field, dark field, variable focus. Meaning probably one of the mode, and especially the confocal mode, will work because with confocal we measure the peak of intensity of the light, meaning we don't have to target the top surface. You can target inside the materials, meaning inside the liquid. If the liquid is transparent, it could be possible, but we have to check. If we have to remove, it's true, replacing and coming back a test rig, it's probably you have some variation. Here we prefer to try passing through the liquid in order to go back and return with a positioning accuracy of 1 micron and not moving the sample or the upper static partner.
Okay. And can resin-based friction materials be tested on MFT 5000?
I don't.
Yeah. In fact, all the results we show are based of resin-based friction material. Yeah.
We are able to measure from liquid to diamond, meaning yes, it will be possible.
Right. So Here we are, and one small question for me: what is the like sample size you require? The minimum sample size for this MFT?
We are actually testing some watch component of 10 micron by 120 micron, meaning we can go from very small to a max size of 48 centimeter, meaning you can put a full brake disc. It's not a problem. It means it's very from, I will say also with the XY table, we can target 1 micron. It means a sample in theory, 2 micron by 2 micron can be targeted.
Okay, right. Wow, wonderful mission. Right, thank you. Thank you, everyone. And thank you, Dr. Carlos, for accepting our invitation for the speaker.
My
And
pleasure.
thank you, Artec Instruments, for supporting this webinar. I would request all the participants to visit the website of our Surface Ventures. We will organize the next keynote on 30th November. So stay tuned in our website, emails, and LinkedIn for further updates. We also have a fortnightly newsletter, uh, a modern surface. By signing up to our mailing list, you will receive it. And we would also ask for your support to take time to advertise these lectures to your contacts. So let us meet again next time. And for now, thanks for joining today, and have a great day.
Thank
Thank
you.
you.
Thank you.
Bye
Bye
bye.
bye.